Alright, so this is our Honors Chemistry lesson video for section 13.1. And so in chapter 13, we surprisingly go back to what you would normally think of that we would cover at the very beginning of the year, and that is states of matter. But now that you know more about intermolecular forces and bonding, we can kind of dive a little bit deeper into states of matter. So in 13.1, we're mainly going to focus on gases. So a gas is a state of matter that forms homogeneous mixtures with other gases regardless of the identity or relative proportions of the component gases. So this is just a really wordy way of saying no matter what ratio you mix them in or what the different gases are, they are going to homogeneously mix together if allowed. A lack of strong attractive forces, and this is referring to intermolecular forces, between particles allows a gas to expand to fill its container. So because the particles are very far apart and moving very quickly and usually only have London dispersion forces that aren't very strong, that's what allows them to spread out if they have a more open space, so if you put it in a larger container. A vapor is a substance that is normally a liquid or solid at room temperature that has been heated to form a gas. So for example, oxygen at room temperature is a gas, so we call it oxygen gas. Water at room temperature is a liquid, but if we heat it to become a gas, we call it water vapor. So that's the difference in a gas and a vapor. They're both the gas state of matter, but a vapor is normally a liquid or solid at room temperature. So kinetic energy is the energy of motion, and so the kinetic theory is based upon the idea that all matter is made up of particles that are in constant motion. So it doesn't matter if it's solid, liquid, gas, plasma, all of them have particles that are moving. And in a gas, they happen to be spread out very far apart and moving very quickly. So the kinetic theory has a few different points that we need to know. So in the kinetic theory, the particles of a gas are considered to be small hard spheres with an insignificant volume. So because a gas takes up so much space, but most of it is just empty space, it's not the particles themselves, we can make our calculations easier by assuming that the particles themselves have no volume in comparison to the total volume that the gas is taking up. There are no attractive or repulsive forces that exist between the particles. Again, they do have tiny forces that can occur momentarily when two particles are passing one another, but if we assume that they're so small it's practically zero, again, that makes our calculations easier. The motions of particles in a gas is rapid, constant, and random. That's true. All collisions between particles in a gas are perfectly elastic. Again, this is an assumption we make to make our calculations easier. A perfectly elastic collision implies that no kinetic energy is turned into another form of energy, like heat through friction or something like that. And so again, it's because the particles are so small and collide for such a short amount of time that such a small amount of energy would even be considered as changing into another form that we can assume it's constant throughout. And then the average kinetic energy of a gas is proportional to its absolute temperature, which is Kelvin temperature. Okay, so the kinetic energy is proportional to Kelvin temperature. So as the temperature increases, the kinetic energy or speed of the particles increases. So the particles of a gas travel in straight line paths until they collide with another object. So it's not like they're going to sit there and go in some curly path. Like it goes straight, it collides, it goes straight, it collides, it goes straight, it collides, it goes straight, it collides. Think about when you're playing pool or something like that. So like I said in the previous slide, during an elastic collision, kinetic energy is transferred without loss from one particle to another, and the total kinetic energy remains constant. In reality, when two things collide, some of the energy is going to turn into heat from friction. But because the gas particles are so small, they're moving so fast, that loss is so little that we can assume it's zero. So gas pressure is the force exerted by a gas per unit surface area of an object. Gas pressure is the result of simultaneous collisions of billions of rapidly moving particles in a gas with an object. So gas pressure is completely based on collisions of particles. The more collisions, the more pressure. An empty space with no particles and no pressure is called a vacuum. And vacuum has two U's in it. Okay, it's not V-A-C-U-M-E. That's the most common misspelling I get. It's V-A-C-U-U-M. All right. And so again, if you have no particles, then there's no collisions and no pressure. And so the more collisions you have, the more pressure. So see here, they would be colliding a lot. They're real packed in there. But as they can kind of spread out, they're going to collide less often. So then there will be a lower pressure inside this container. So how do we calculate gas pressure? Well, pressure is force over area. So pressure will be in pascals. That's a unit of pressure. We're going to learn multiple units of pressure in this chapter. F is force, which is in newtons. A newton is just a kilogram times meters per second squared. So it's just a combination unit. It's a derived unit. And then A is area. Area will be in meters per second squared. Now sometimes you might need to calculate force. So if you've forgotten how to do that from either physical science or physics, force is mass times acceleration. So of course force is F, it's in newtons. M is mass, it's going to be in kilograms, because remember a newton is a kilogram times meters per second squared. And A is acceleration. Now normally we talk about acceleration due to gravity as 9.8 meters per second squared on Earth. Now of course if they gave you a different acceleration you would use that. So air is a complex mixture of several substances. It's primarily nitrogen, which is 78%, and notice it's N2 because it's a diatomic, hopefully you remember that, and oxygen, which is also a diatomic, O2, and it's about 21% oxygen. So even though we actually need the oxygen to breathe, most of our air is actually nitrogen. And then of course small amounts of several other gases, and so you can see there's some argon, there's of course carbon dioxide because that's what we exhale, and that is also a main pollutant in burning things like fossil fuels. So air exerts pressure on the earth because gravity is constantly trying to pull our air downwards. That's why we keep our atmosphere. Atmospheric pressure decreases as you climb a mountain because the density of Earth's atmosphere decreases. That's why if you ever go to a different place, like a mountainous region, and like you're a runner, if you ever try to run and you're at a much higher elevation, you have trouble catching your breath, that's because that air is less dense. So when you're breathing in, you're just not getting as much oxygen as you would at sea level. And so because the air is less dense, there's less pressure, less air pressure. That's why also, if you bake a lot and you use like box cake mixes, if you ever look, there's usually high altitude directions on there where you have to alter some things, and that's because air pressure affects boiling point, which we'll talk about in a little while, and so that's why you have to alter things in that recipe because it's going to boil at a different temperature, the density of the air just messes everything up. So how do we know what air pressure is? Well, we use a barometer. So a barometer is just a device used to measure atmospheric pressure. So it's like a really long, thin test tube that's closed on one end and open on the other. So you fill the test tube all the way with mercury, and then you cover it up. And obviously, mercury is poisonous, so you would need protective equipment on when you do this. And then you flip it over into a pool of mercury. Well, if you look, this was all mercury, but what's going to happen is some of it's going to come out into the pool. So it's going to sag a little bit. So what's up here is actually nothing, so it's a vacuum. So we have a vacuum up here. Well, what's keeping the mercury in the tube? Well, that's the air pressure. So if we add more air pressure and press down more, the mercury actually rises up in the tube. If we add less air or take away air pressure and have lower pressure, then more of it will come down. So it kind of goes up and down like a thermometer, but instead of measuring temperature, it's measuring the air pressure on that pool of mercury. So the SI unit of air pressure is the Pascal, which is PA, and a Pascal is just 1 Newton per meter squared, because of course Newton is force and meter squared is area, the unit for area. So the most common units of pressure are actually atmospheres, millimeters of mercury, kilopascals, and torr. So even though the SI unit of pressure is Pascal, in here we'll actually use kilopascals a lot more, because 1 Pascal is just a very small amount of pressure. So this is how all of those pressures are related. So this is like our pressure conversion factor. So here, let me put it on the board so that way I don't have to keep clicking back to this slide. So 1 atm equals 760 millimeters of mercury. Millimeters of mercury is what they usually use for pressure when you go to the doctor, like blood pressure. Equals 101.3 kilopascals equals 760 torr. So these are how all of our pressures are related to each other. So let's look at how to convert between these. All right, so I'll show you the top one, maybe even the top two, but just make sure you try one on your own at some point. So it says convert 0.357 atmospheres to torr. And by the way, ATM is the abbreviation for atmosphere, not atom. So I'm trying to go from atmospheres to torr. Now the thing about this conversion factor is you don't have to like work your way across, like go from atmospheres to millimeters of mercury to kilopascals to torr. You just find whichever two you need and pull those two down. So I can see that 1 atmosphere equals 760 torr. I don't need to use millimeters or kilopascals. I don't need either of those. So I start with what I know, which is 0.357 ATM. Alright, and so then I follow my golden rule. So hopefully you have gotten way used to doing the golden rule at this point. So since I have atmospheres on top, I'm going to put my 1 atmosphere on bottom. And I'm trying to get to torr. So 1 atmosphere equals 760 torr on top. So see, now atmospheres cancel. I made it to torr, and so I'm ready to solve. So since both numbers are on top, I'm going to multiply, and when I multiplied, I got 271.32 torr. That's a lot easier than stoichiometry, right? Alright, so if you feel comfortable, try the next one. Otherwise, try the last one. Alright, so let's look at this one. So we're going from torr to ATM. So I can see that 1 ATM, again, equals 760 torr. So I don't need the millimeters of mercury or the kilopascals. So I start with what I know. I have 6.6 times 10 to the negative 2 torr. So I just follow my golden rule. The golden rule says torr has to go on bottom this time. How many torr? 760 torr. And that equals 1 atmosphere, or 1 ATM. So my torr cancel. And then since I have 1 number on top and 1 on bottom, I'm going to divide. I'm going to do 6.6 times 10 to the negative 2 divided by 760. And so I ended up getting 8.68 times 10 to the negative 5 ATM. Alright, so definitely pause and try this last one real quick. I'll assume you've done that, and let's look at it together. So this one says convert 147.2 kilopascals to torr. So this time I'm not interested in atmospheres. I'm interested in kilopascals and torr. So I can see 101.3 kilopascals equals 760 torr. So I start with what I'm given, 147.2 kilopascals. I follow my golden rule. If kilopascals is on top, kilopascals goes on bottom, and it's 101.3 kilopascals. And that, of course, equals 760 torr. So see, you're not always going to have a number that's a 1. Kilopascals cancel, so I multiply my top 2 numbers. This is just like stoichiometry, except way easier. I divide by the bottom, like the math works the same. Multiply the top, divide by the bottom. And so I ended up getting 1,104.36 torr. Alright, so hopefully you got that one right. So see, like I said, the math is way easier than stoichiometry, but it's the same basics of converting, following the golden rule, things like that. Like, trust me, eventually you're going to love the golden rule if you don't already. Like, it just makes everything so easy in life. Alright, so let's look at a couple more. So again, maybe start trying some of these on your own. So in countries that use the metric system, such as Canada, atmospheric pressure in the weather reports is given in kPa. Convert a pressure of 745 torr to kPa. Alright, so I'm going to assume you paused it and tried it. So we're going from torr to kPa. So again, I'm going to use the same 2 sets. 101.3 kPa equals 760 torr. So I start with what I know. I have 745 torr. And I follow my golden rule. Since torr is on top, torr goes on bottom. So 760 torr goes on bottom. And 101.3 kilopascals goes on top. So torr cancel. I multiply my top 2 numbers and divide by my bottom one. And so in this case, I got 99.3 kilopascals. Alright, now this one I kind of give you a new conversion factor in the problem. However, y'all, once you know how to follow the golden rule, you should be able to convert anything I ever give you as long as you know the conversion factor. Okay, so again, just pause this one and try it yourself, even though I haven't showed you one like this, because you know how to follow the golden rule. All right, so I'm going to assume you tried it and got it right, so let's check it. It says an English unit of pressure sometimes used in engineering is pounds per square inch, which is pounds per square inch, or they'll abbreviate it as PSI. Well, 1 atmosphere equals 14.7 PSI, or pounds per square inch. If a pressure is reported as 91.5 PSI, express this in atmospheres. Okay, so I don't need to use this for this problem because they gave me the conversion factor right here. 1 atmosphere is 14.7 PSI. But we're starting with 91.5 PSI. Okay, so I follow my golden rule and I know pounds per square inch, or PSI, needs to go on bottom. So how many? 14.7 PSI. And you're more than welcome to write PSI or pounds per square inch. It doesn't matter. I just use PSI since they gave me PSI. And so 14.7 pounds per square inch equals 1 atmosphere. So my PSI cancel. And so I'm going to take my 91.5 and divide by 14.7. And I ended up getting about 6.22 ATM. And so again, y'all, once you know to follow the golden rule, you should literally be able to convert anything that you're ever given for the rest of your life. Because the golden rule never changes. That's why I call it the golden rule, because it's always the same. There's no exceptions like there is to everything else in life. So the next thing we need to learn is how to use a manometer. So a manometer is a device that we use in the lab to measure pressure. So pressure is based on a difference in the height of the 2 arms. So in a manometer, you have your reaction vessel. So your reaction would be occurring in here. It might produce a gas, or you might just have a gas in that vessel. And then you have this weird S-shaped arm that's open, but it can be closed. Okay, we'll talk about that later. But it's like a tube. And then it has mercury in it. And so we have 2 different heights on this tube. And so that's what we're kind of looking at. Like, are the levels equal? Was one side higher? Is one side lower? That's what we're basing the pressure on. Now, when it's open, like this one, see how it says open end? It'll tell you if it's open or closed, by the way. When it's open, we have to take into account atmospheric pressure, because atmospheric pressure is pressing in on this side. When it's closed, you don't take into account atmospheric pressure. Okay, so the pressure of the gas is the pressure from the atmosphere. So P of gas is our pressure from the atmosphere plus the height of the mercury. Okay, and so again, they'll have to give you the height. So I'll show you what I mean in like the next question. So it says, a sample of gas is placed in a flask attached to a manometer, and the level of mercury in the open end arm has a height of 136.4 millimeters. And the arm that is still in contact with the gas has a height of 103.8 millimeters. What is the pressure of the gas in ATM if the atmospheric pressure was 764.7 torr? So the first thing that we have to take into account is we need to convert. They're giving us millimeters of mercury for our height, but then they give us torr for our atmospheric pressure, but then they ask us what's the pressure in ATM. Okay, so first of all, let's talk about these 2 heights. Okay, so I'm going to click back so we can actually see our picture. Okay, so what it's saying is, it says the level of the mercury in the open-ended arm has a height of 136.4 millimeters. So that would be this side. So this is 136.4 millimeters. And the arm that is in contact with the gas has a height of 103.8 millimeters. So that would be this side. So this is 103.8 millimeters. So I can take the difference of that to get the height. All right, so what I do is I take the 136.4 and I subtract the 103.8. And so I get that my height is 32.6 millimeters of mercury. Okay, so see, that would be this right here. This will be my 32.6 millimeters of mercury. All right, but here's where the trick comes. Again, they gave me millimeters of mercury for the height, but they gave me atmospheric pressure in kilopascals, but yet they've asked me for my answer in atmospheres. So we got to get everything on the same page here. Okay, so we have that our atmospheric pressure, it says, sorry, I don't have my slide up anymore, so I'm having to look here. It says the atmospheric pressure is 764.7 torr. So I need to add my atmospheric pressure and my pressure from the height of the mercury. Now before you waste time converting one of these into the other one, what I want you to notice is 760 millimeters of mercury equals 760 torr. So in our conversion, millimeters of mercury and torr are actually the same thing. Okay, so I don't actually need to convert one of those into the other. So once I add those together, I get 797.3, and then I just chose to keep torr. You could have kept millimeters of mercury. It doesn't matter. Neither of those are the right unit. All right, so it has asked me what is the pressure of the gas in ATM. So then I would need to take this and convert it to ATM. So we need ATM and we need torr. So 1 ATM is 760 torr, so I follow my golden rule as always and put torr on bottom. So 760 torr is 1 ATM, so my torr cancel, and so then I just divide. And so I ended up getting 1.049 ATM. Okay, so again, just to recap, we saw the two heights of our mercury. It explained that in the question. We subtracted to get the height, and then we did our pressure from the atmosphere plus our pressure from the height, and we got our pressure of our gas, but it was in torr or millimeters of mercury, and so then we just converted it to ATM. Okay, so y'all just know it doesn't matter whether you like converting or not. It's never going away, so you might as well at least get good at it. I mean, whether you like it or not is around. All right, so maybe try this one. It's just a conversion problem. And I'll assume you've done that. Let's look at it together. So it says convert a pressure of 0.975 ATM into pascals and kilopascals. Okay, so see, we're going from ATM to kilopascals here. All right, so let's start with our ATM. So we have 0.975 ATM. So I follow my golden rule. ATM has to go on bottom. How many? 1 ATM equals 101.3 kilopascals. So my ATM cancel, and so then, let me get on the right page. And so once I multiply, I get 98.77 kilopascals. All right, so we got kilopascals, but we also need to get pascals. Well, kilo is the same prefix regardless of if it's kilometer, kilogram, kilopascal. It doesn't matter. Kilo always means 1,000. So here's my answer for kilopascals. You can either just move the decimal if you know how to do that, or then you just need to convert. So 1 kilopascal is 1,000 pascals. So I would just multiply it by 1,000. So I get 98,770 pascals. Just like that. So hopefully you got that one right. All right. So as a substance is heated, its particles absorb energy, some of which is stored within the particles. This increase in kinetic energy results in an increase in temperature. So kinetic energy and temperature are directly proportional. The particles in any substance at a given temperature have a wide range of kinetic energy. So even though I might have a glass of water and I say, oh, this is at 25 degrees Celsius, it doesn't mean that every single water molecule in that glass of water is moving at the exact same speed. The temperature is the average kinetic energy. So although the particles in a sample of gas have an average kinetic energy and hence an average speed, the individual particles move at varying speeds. So like if you look here, we can take the average speed overall, but you can clearly see that some of them are moving faster than others at certain points. So the root mean square speed, or the RMS speed, which is represented by a U, is the speed of a molecule possessing average kinetic energy. So the RMS speed is not quite the same as average speed, but the difference between the two is very small. So as temperature increases, RMS speed increases. So the important thing to remember is that the speed of the particles is based on the temperature. Okay, it's based on the temperature. So let's look at a question together. So it says a sample of O2 gas initially at STP is compressed to a smaller volume at constant temperature. Okay, now sometimes in like a regular class, whether something's constant or not, it's just kind of like, oh, that's just extra information. In here, when it tells you something's constant, it's usually super important. So it is at constant temperature. What effect does this change have on? Okay, so we have reduced the volume, but we have kept temperature constant. So what effect does this have on the average kinetic energy of the O2 molecules? Well, remember, kinetic energy is directly proportional to temperature. Temperature remained constant, so average kinetic energy is not going to change. So your kinetic energy stays the same because it's based on temperature, and temperature didn't change. All right, it says, what effect would this have on the average speed? Well, remember, the speed is based on the kinetic energy, which is based on the temperature, which remained constant. So the speed does not change. Both of these are related to temperature. So unless it tells me temperature changes, those are not going to change. All right, so same question, but there's a couple more parts on the next slide. So it says the total number of collisions of O2 molecules with the container walls in a unit time. So are the collisions going to increase? Well, we did decrease the volume of the container. So since we squeezed the particles into a smaller area, of course the number of collisions are going to increase because we decreased the volume. So the total number of collisions will increase because we decreased the volume. And then the last one says the number of collisions of O2 molecules with a unit area of container wall per unit time. Wow, don't you love how they word these things? All right, so again, this is about collisions. Because we decrease the volume, it's going to increase. So the number of collisions increases again because volume is decreased. Okay, so remember, speed and kinetic energy of the particles are based on temperature. So if it has something in there that says temperature is constant, like this one did, then those are not going to change. All right, so let's move on. Now that I know I just have the answers up here, I'll just keep clicking instead, right? So save some expo markers. I've used up so many expo markers in these movies, you don't understand. So how is the RMS speed of nitrogen molecules in a gas sample changed by these things? Okay, so we're looking at how would these things change the RMS speed or the average speed of the nitrogen molecules. An increase in temperature. Temperature does affect speed of the particles. Remember, they're directly proportional. So if we increase the temperature, we're going to increase the speed. So if we increase temperature, RMS speed also increases. It says if we increase the volume. Now, increasing the volume is going to decrease pressure. It's going to give the particles less chance to collide, but it's not going to make them move any faster or slower, so it would have no effect on the speed. No effect on the speed. So this would affect pressure, it would affect the number of collisions, but it's not going to affect the speed. How would the speed be affected by mixing with a sample of argon at the same temperature? Okay, again, speed, kinetic energy are based on temperature. Temperature is remaining the same, so there would be no effect. Again, it would increase the pressure because now there's more particles, there would be more collisions, but the speed of the particles will not be affected. So kinetic energy and Kelvin temperature are directly proportional. Directly proportional means they do the same thing. If one goes up, the other goes up. If one triples, the other triples. An increase in average kinetic energy causes the temperature to increase, and a decrease in average kinetic energy causes the temperature to decrease. So in other words, the faster the particles are moving, the higher the temperature, and as we cool it down, they start slowing down. And then eventually, they slow down and slow down and slow down and stop. So absolute zero is the temperature at which the motion of particles theoretically stops. So there is no zero, there is a zero on the Kelvin scale. There's no negative on the Kelvin scale because you can't go slower than stopped. So you can't get any lower in temperature than 0 Kelvin because temperature is based on the speed of the particles. So, section assessment. Briefly describe the assumptions of the kinetic theory. Alright, so the kinetic theory, I'm going to abbreviate all of them, says that the particles, basically we can assume they have no volume. The particles are moving so fast and so far apart, we can basically assume they have no forces, attractive or repulsive, between them. They are in constant motion though, rapid, constant, random motion. And when they collide, they have perfectly elastic collisions, which remember that means that we assume that such a small amount of energy is changed to heat as a result of friction that all the energy just remains as kinetic energy. So perfectly elastic collisions. All right, number 2. How is the Kelvin temperature of a substance related to the average kinetic energy of its particles? It is directly proportional. Directly proportional. And remember, if you're worried you're not going to remember what directly proportional means, however, you do need to get used to phrases like that, you can say that as kinetic energy increases, then our temperature increases. So number 3, it says convert the following pressures to kilopascals. Alright, so we're going to use our conversion up here. So we have 0.95 atm. Wow, I love how I just erased those two. So we're going from atm to kilopascals. So 1 atm is 101.3 kilopascals. So I start with what I know, which is 0.95 atm. And then our golden rule says if I have atm on top, I'm going to put 1 atm on bottom. And that equals 101.3 kilopascals on top. So my atm cancel. Since both numbers are on top, I'm going to multiply. And so for that, I end up getting about 96.235 kilopascals. Alright, so maybe pause it, try this one first, and then we'll look at it together. So we're going to convert 45 millimeters of mercury to kilopascals. So this time I need millimeters of mercury and kilopascals. So 760 millimeters of mercury equals 101.3 kilopascals. So I start with what I know, and that's 45 millimeters of mercury. And so then I follow my golden rule. Since millimeters of mercury is on top, I'm going to put 760 millimeters of mercury on bottom. And that equals 101.3 kilopascals. So our millimeters of mercury cancel. And so then I multiply my top two numbers and divide by the 760. And I get about 5.99, which you're more than welcome to round to 6, kilopascals. Alright, so that is what we need to know about gases right now. So the hardest part about this section is usually the converting of pressures and those manometer problems, especially the manometer problems. I didn't have an example with a closed arm on the PowerPoint, however we will do some examples in class, so make sure you pay attention to that. The closed-ended ones are even easier than the open-ended ones though, just saying.